Thanks everyone for coming to my session. I'm Wei Wei. I'm a managing director at Accenture. So today I'm going to talk about crafting domain-specific large language models with enterprise data. All right. So here is today's agenda. So we're going to introduce some of the stuff about the applied research team at Accenture, our Accenture foundation model efforts, and our strategy for model training and model fine-tuning. And we'll deep dive into a specific use case, which is the ESG domain specific model, which we recently released at Davos this year. All right, so we have a newly established research team at Accenture. It's located in Mountain View in California, just roughly 30 miles away from this location. And it's the first AI research lab in the consultancy industry. And the reason we established this research lab is because we recognize the need for AI talents, especially in the field of large language model and the foundation model building. And our team is established with 3 missions. And number 1 is definitely to advance the state-of-the-art research and innovate the engineering to really accelerate many of the model building and our client engagement at Accenture. And number 2, to provide really the forward-looking thinking on how AI and especially generative AI will disrupt business for our clients. And thirdly, our team connects the Accenture with the broader research academic community to co-drive and also lead some of the research agenda that will generate a longer-term impact to not only academia, but also the industry in general. Right, so far we have many people that we hired from top academic institutions and also industries. Many of them has years of experience in foundation model training, large language model, and ML infrastructure. Okay, so the goal here is really to hire the best in the industry and to concentrate the talents in Mountain View and to help our clients and help our company to innovate in the space of a foundation model and the large language models. All right, so we'll talk about some of our strategy for model training. So one of the projects we lead with, which is we call Accenture Foundation Model Efforts, is our model customization initiative within Accenture. And when we talk about model customization, we will have to talk about a very important topic, which is called domain shift, right? So that is basically, we're asking ourselves, why do we ever want to consider fine-tuning our model? Is the base model, either from OpenAI or from open source, become bigger and bigger, and as the model iteration going on, a lot more information will be embedded. Then why do we still want to fine-tune our model? Well, the reality is the knowledge we use for training our base model is only a tiny fraction of the knowledge present in the entire world. Think about many of the models are trained using 3 to 10 trillion of tokens, right? But if you think about how many data are there over the internet, this is a tiny fraction of them, right? So because we are limited by compute, right, and also the amount of resources we have, the current base model can only capture many of the common sense knowledge, things like trivial QA, math question answering, and also some of the bar examinations, right? Those are not really the knowledge that we will need from an enterprise perspective. In the enterprise domain, we are looking at stuff like sales and origination, finance, business operations, right? Those are the knowledge we will have to acquire in order for the large language model to function in a domain-specific setting. And the goal of the fine-tuning, in one of the perspectives, is to conduct something we call domain transition from a base domain defined out by the set of data set we can have, all the way to the target domain, which is defined by the data set from our client or from the business settings. And a couple of things we can achieve by model fine-tuning. One is really the reduced cost. You can achieve better performance compared to the base model by fine-tuning using a much smaller model. That will save you a lot of money in terms of inference cost. In our experience, we can save up to 10K to 10x to 20x amount of compute bills when we're conducting inference, just because the model is significantly smaller. There are other benefits of doing model-specific, domain-specific fine-tunings, things like model performance, which is essentially the quality on a specific domain, and also security and the compliance considerations, which we will have to use a set of data that's specific to a set of domain that we know are safe from a legal perspective. Okay, and in terms of fine-tuning techniques, this is the point of view we have on model customization. If you really think about how the large language model is trained, there are two specific steps. One is something called pre-training, which is actually step 2 here. The other is called instruction fine-tuning, right? And then when we're conducting the domain-specific fine-tuning, we're also dividing into 2 steps. The pre-training, which is called close pre-training, will give you new knowledge, right? This is the big circle on the right-hand side. Versus the instruction fine-tuning will not give you that much of new knowledge, but will give the model a new way to interact with human, right? So the instruction fine-tuning really tells the model how to provide new ways to interact with humans, things like a Q&A, multi-turn conversation, or maybe a customized ways for conducting such a conversation models with human. Those will fall into instruction fine-tuning. Whereas if you are thinking about medical data, financial data, those will be the new knowledge injection that it will have to go through continuous training. And in our experience, you don't need a lot of data for instruction fine-tuning. You can get away from something around 10K to 30K data point. But the instruction fine-tuning data has to be carefully labeled, right? Versus the post-pre-training, you don't have to label them, but you really need a large amount of data in the scale of tens of millions of data to get started in order to generate any impact for knowledge shift from the base model. Okay? All right. And then we can talk about some of the newly released model from Accenture, which is in this case a ESG model, and we will go through the entire lifespans of model customization and the model training in this case study. Okay, a single slide of the highlight of the ESG model and why ESG reporting is a problem that we're solving using large language model, right? So ESG reporting, which is called environment, social and governance report, is required by every company that is public in the United States. And a different country has different requirements. For example, US has one requirement. In the EU, in the UK, they have a different requirement for reporting. It's a tedious procedure that every company will have to do every year. Usually takes a team of 30 to 50 people with an effort of roughly 1 quarter to finish this report. And some of the report can be very lengthy, up to several hundred pages long, right? And the report, they have to confirm with certain standards, the tune of the language, the sections. In our model, we actually analyze 12 different sections, right? And those are some of the requirements. And the goal here is to build a large language model that specifically generates ESG report by using the language commonly found on the ESG reporting and organize the structure of the article correspondingly to the ESG report, right? And here are some of the highlights here. We consumed roughly 15K ESG report. We collected it globally, which roughly 7.5 million data annotations on those reports. Those are trained using roughly 16K hours of Accenture's compute using our distributed training infrastructure, and support multiple interactive patterns such as generation, which will actually ask the model to generate a ESG report or a Q&A, okay? And then we will see some of the evaluation result on productivity gain and also the quality gain compared to the human evaluation on our control experiments. And here is a sample input-output pair from the ESG reporting. The input looks like this: generate a section of the sustainability report for a specific company, right? And here are some of the talking points, which is the KPI, if you are familiar with the ESG reporting, right? The goal is to convert this KPI and the natural language request into an article that is compliant with the ESG reporting, which is on the right-hand side, right? We develop basically 4 paragraphs based on the ESG KPI on the left-hand side, and all of them needs to be developed and organized in a few paragraphs here on the right-hand side, right? So this is the input-output, and the whole point and the major goal of the model training is to, one of the goals is to prepare such a data set from the input-output pair so that the model can learn this entire new capability compared to the base model. Okay. And we also developed our tool for data annotation. As you probably realize, this process is, many of them is heavily manual. In reality, we actually deployed a machine plus human procedure. But this is what the machine procedure looks like. We have the ESG report on the left-hand side. This is the actual PDF. As you can see, the report scope, boundaries, reporting history. Those are taken from the actual report, right? And the goal here on the right-hand side is to annotate which page contains the section for the ESG report. If you look at on the right-hand side, we have I think the environment stewardship. This is one of the sections commonly found on the ESG report, and also the government section is also commonly found on the ESG report. We'll just need to map each of the section we supported to the page from the training data. This is one of the annotation tasks we do. Of course, we have a wide range of them, but the goal here is to collect high quality data, which is not easy just because even for people who look at the report on a daily basis, it's not trivial to find out which report, which section belongs to which, right? So that's one issue. The other issue is some of the report can have non-standardized sections. They have many sections, 2 sections collapsed into the same. And those are the issues we see when we do data annotation. So in reality, we employed more than 2 annotators for each of the sections. If they do agree, then we consider that as a valid example. If they don't, then we have a third person to look at it. So this is our data annotation procedure. And in terms of model training, we require efforts more than just human annotation because humans are really expensive. And in order for the model training to scale, we can rely completely on the annotation. So in reality, we use a human plus machine scheme. So this is a paradigm that we actually use a base model, which is the Mistral model here, for conducting the KPI generation. As you see, from the input-output pair, the input consists of a set of KPIs, right? And using the base model, we can extract those KPIs out of the model. That will be formed as the first step of data creation. And then we will send the data set for human, and they will do the further verification. Okay, so the first step is to conduct the KPI. And unfortunately, as with many base models, using machine to generate such an annotation, which we call pseudo annotation in a large scale, is not always reliable, right? So here's what we can see: the raw text to KPI ratio. This is in the ratio on the x-axis is the ratio, and the y-axis is the count, right? As you can see, it forms some sort of a single peak distribution with the majority of the KPIs falling into a ratio of roughly between 1 and 2, right? I will explain a little bit later on what that means, but if you really look into it, you will find many of the anomalies. For example, many of the results we have very long KPIs, which means the ratio is very small. And if you look at some of the result, right? So for example, the first one will be a KPI that's generated by the large language model. is too short, right? So it doesn't really help us, right? And we did multiple techniques, including prompting, to improve it. And on the bottom, you see a well-developed KPI. This is what we want, right? So those are some of the techniques we will have to employ in order to prepare our training data. And of course, everything will go through human for a second round of checking in order to make sure the quality of the data actually meets the bar for training large language model. And of course, you can have KPI that is too short, which means the ratio is too large, right? So in reality, we don't want it to be too long or too short. And we have a very strict data filter that only keeps something in the middle, right? This is one of the key in training any foundation model. Since the base model, when you train it, it has a very high quality bar for data set. When you do the fine tuning, you need to make sure that the data should be at least as decent as the one you use for the base model training. Okay. And after we have the KPI extraction, this is really the first step for data preparation. Then we go through two steps. One is something we call the KPI to raw text. We basically prepare the input-output pair from the KPI all the way to the text we take from the article. And the other one is something we call the KPI to generated text. This is basically we retrieve the same answer from the base model, which basically we're repeating the knowledge already in the base model. Well, I will explain why in a minute why this is necessary in addition to the data set we have. Okay, so this is the KPI to raw text. As I mentioned before, the first step is to really generate the KPI, and the second step is to put together the text corresponding to this KPI. For example, on the right-hand side, this is the environmental stewardship section. We generate the KPI based on the previous step, and then we put them together to form a single data sample. This is the actual data we use for training, and we have hundreds of thousands of them. Okay. And this is the knowledge the machine will learn from the PDF and from human annotation. And we have another set of knowledge, which is basically we use the prompt of those KPI, and we prepare the output from the base model, right? Why are we still interested in a data set like this? It's because when you are doing the domain-specific fine-tuning, there's a phenomenon called catastrophic forgetting, which means the more you learn on the new knowledge, the more you actually forget on the old knowledge. And in order to mitigate catastrophic forgetting, we keep balance between the knowledge from the model, which is this one, right? Knowledge from the base model, and the knowledge from the new domain. We have a balance between these two so that the model doesn't forget as much. Right? This is a key technique when we do any domain-specific fine-tuning, especially when your data set is small compared to the one used in the base model. And also when your target domain is deviate a lot from the base domain, then in these situations, you will have to use techniques to prevent forgetting from happening. The one we use here is something called data replay. There are other techniques you can use, for example, regularization on the model in order to prevent such from happening. But in our experience, this is a must in order to make sure that the model has certain capability for generalization that goes beyond the small amount of training data you have. All right, and we, of course, use NVIDIA GPU using our own proprietary distributed training infrastructure, and we fit both of the two data sets, the KPI to raw text, which is the new knowledge, the KPI to gen text, which is the old knowledge. We've mixed them together and fit that into the base model. In that case, this is the Mistral model. And of course, the training will generate the set of new model weights coming out of the training procedure. And one important factor here is the safety guardrail. As with any generative model, it's not guaranteed the model will generate safe and also consistent answers. So I think we employ the Azure content safety here. I believe this is on the input checker. If you send a prompt that the model deems to be unsafe, it will just intercept this response without sending that to the model and give you a warning sign basically tells you this one of the prompt is not safe. We should not proceed for the generation procedure. Okay, now here's some of the result. We evaluate the model by two standards. The first one is really look at the productivity gain. So basically, the productivity gain is compared by doing the control experiment of having the machine to generate the article and using human to edit it versus using human to come up with the article from scratch, right? As you can see, there are roughly 75% of productivity gain compared to the baseline, which is writing the article from scratch. And on top of that, there's also a significant productivity gain here, which we see from the result on the December version is roughly 21% on the quality gain. I'm sorry. So basically, on 21% so the machine generated text is roughly 21% higher in terms of our quality metrics compared to the human generated ones. And least but not, but also a very important point is on the hallucination, as this is one of the main issues with any large language models. We basically counted the amount of KPI in the input and the output. So if you see the result along the line, then it means the model is doing a good job. That means you have the same amount of KPI from the input to the output. As you can see, as we iterate the model, all the way from the earlier version to the later version, the model performance improved dramatically for this hallucination analysis. Okay, this is the end of the talk. I'll just open for the questions.